I just want to introduce myself. I'm Gail Allen. I'm the Vice President for Education and Young Professional Committee for the AAS. And as our President said, Carol, this morning, I want to talk a little bit about the Macauley Award, as this is the first time that we're offering that. And as you know, if you worked with Molly, this is to honor a national leader in environmental economics who helped to many years to establish, lead, and guide research projects combining economics with space research. Her fields of interest goals were broad, including relatable, renewable energy, new technologies and natural resources, and most of all, helping decision makers understand the economics of space. So this award is in two tracks, so you're going to hear from two speakers. It's really to recognize graduate and undergraduate students majoring in science and engineering, one track, or in business and space policy, the second track. And I just want to quickly go through what the process was, because it was a very rigorous process. We actually made a call, issued a call for abstracts in early this year, and I have to give kudos to all of the AAS members who were willing to give their time and volunteer to review the abstracts, as well as we had invited the down select of the abstracts to submit papers. The AAS members in both tracks were very generous of their time in reviewing the papers. And then the third step is that we actually had virtual oral presentations, of which the AAS members participated in that to make sure that the awards that we were given for this Macauley Award were well deserved. So, like I said, we have two speakers today, the winner from each of the tracks. The first that will speak will be Miguel Ramirez, who actually won the Science and Engineering track. He's from Purdue University. His talk is going to be on modeling for mechanical responses to composites. So, Miguel, you want to come up? Please welcome.
All right, so thank you for the introduction, and I want to say that it is an honor to be here at the American Astronautical Society to present this work, and especially for the Macauley Award. So let's go ahead and begin with the slides. Well, I can, okay, there we go. All right. So there are 3 points to be made here. The first point is that it is expensive to launch mass into space, and the numbers here speak for themselves, since it can take anywhere between $1,400 to $13,000 to launch a kilogram of mass. The second point is, therefore, that mass is a key consideration in designing aerospace structures, and reducing mass is desirable. Lastly, we want to design with lighter yet strong enough and durable materials, so we seek for desirable candidates for lightweight structures and new forms of advanced composite materials. Now, there are rules in place for designing aerospace structures. One of these rules deals with the insertion of new materials that require a substantial cost penalty associated with satisfying the rules and regulation of proof testing to ensure safety. And so efficiency of new material application directly influences the timeline of the subsequent stages of product development. Therefore, efficient and well-informed key decision points need to be made, and these may be assisted by leveraging technological advancements. So a crucial question to ask ourselves is, how can we further improve the efficiency of decision-making within these phases of design when using advanced composite materials? And two significant areas have been identified, which these are the use of extrusion deposition, additive manufacturing of composite molds and tools, and a virtual laboratory framework for advanced composite material performance characterization. Now, the motivation here is for the fabrication of parts which are complying with the aforementioned rules, yet at a reduced time and cost. These structures and considerations are those with 3D geometrical complexities, as shown here, and that can be compression molded to replace structural metallic parts. And that is shown over here. And so compression molding can be used for the production of near-net shape parts with minimal machining, thus making it time effective. Here, additive manufacturing further contributes to the time and cost savings by rapidly producing compression molding tools with minimal machining requirements. And so simulation empowers the widespread confidence adoption of these technologies and enhancements of their process efficiency. And you can see a close-up image of how this material looks when you compression mold them. And complex physics, multi-physics phenomenon are involved in a typical additive manufacturing simulation process and govern the quality of the overall process outcome. Understanding and controlling the complex physics through simulation helps in achieving the desired quality. Not only should we leverage extrusion deposition additive manufacturing technologies, but also the processing simulation, since it is paramount for process quality. A brief description of the simulation workflow is shown here, actually. And the first stage deals with the geometrical construction of the tool and the corresponding layer slices needed for the machine. Secondly, the EDAM process simulation numerically analyzes temperature, polymer phase changes, and residual stress evolution, which collectively may change the desired shape of the printed part and negatively influences performance. Therefore, the essence of simulation is to alleviate the trial and error fashion of printing parts. And to enable processing simulation, machine and material characterization is required. The focus here is on making the material characterization process more efficient by developing a computational framework for supplementary virtual characterization. And so multi-scale analysis allows to evaluate how the details of material composition affect the material mechanical properties. Additive manufacturing process results in a composite having short discontinuous fibers suspended within a matrix with voids present. Hence, the microstructural details such as fiber orientation, fiber length and diameter, fiber arrangement, fiber volume fraction, void volume fraction, properties of the fiber and matrix all collectively define the macroscopic response of a short fiber composite. Moreover, the microstructure itself is dependent upon the manufacturing specification. As soon as the microstructure of the material is quantified, a computational model can then be used and developed. And so here, I want to present to you the proposed computational workflow to virtually characterize the mechanical response of a short fiber composite. A boundary value problem needs to be solved with finite element method, with the workflow outlined in the present slide. And the pre-processing stage deals with the development of a virtual microsample based on experimental statistics. Then appropriate constitutive models are specified for the microphases alongside damage mechanics to simulate the progressive failure and suitable boundary conditions. Lastly, this finite element analysis is carried to obtain the composite properties. So you need two things. You need experimentation in order to do the computational analysis. And so experimentally measured statistics of the composite microstructure is a necessary input for a computational model. It was acquired through the analysis of microimages of two kinds. The first was obtained by polishing a section of a printed material, and the second type was obtained by placing dispersed fibers onto a glass slide. A physical mechanical tensile test according to ASTM D3039 is carried to obtain the macro stress and strain of this material and compare with microsimulation results. And so the behavior of matrix fiber and this interface are mathematically described by various computational methods. And this is all shown here. Now, what I'm showing here is the evolution of the homogenized stress-strain response of a virtual microsample. And this is shown on the dynamic plot to the left, and the corresponding progressive failure of the sample is shown on the right. Nucleation and maturing of the fiber matrix interfacial cracks and matrix cracking can be observed as more tensile loading is applied on the virtual material microsample. The progressive buildup of local damage then leads to a gradual loss of the composite stress carrying capacity, which eventually culminates into the ultimate failure event when a critical amount of damage is accumulated in the material, splitting it into two pieces. Therefore, the simulation provides an insight and allows to harvest the knowledge of how the composite microstructure derives the failure process, and we can calculate the stiffness and strength characteristics from that. Now, the developed simulation framework is rooted in the well-grounded physics principles, which allows to obtain the realistic simulated results that match closely with experimental data. In this slide, this is precisely what we're showing. Good agreement between experimental results and simulation, which further shows us the power of leveraging these tools. Now, We're going to switch gears here and talk about the second point and elaborate on the key area dealing with a virtual lab framework for advanced composite materials. PPMCs are cut-out forms of continuous fiber laminates, tape, or prepreg, and these can be stochastically deposited into a mold to make a part. Likewise, these same materials can be arranged and engineered in a particular fashion. Now, we have discussed how using these new forms of lightweight composite materials such as chopped prepregs for compression molding can benefit the cost savings with lighter yet stronger material with fast manufacturing cycle and less machining as in metallic parts. The challenge here is to develop a database of mechanical properties for a new material system as it is necessary to design the parts. The cost of the material characterization can be reduced if some of the testing is done virtually by means of simulations. And so digital twins of standard mechanical tests can be used to virtually characterize the composite system. This would aid in the acceleration of material certification and reducing the physical test matrix. Virtual material samples are configured to the required shapes and subjected to the appropriate loading and boundary conditions. So fundamental knowledge of material behavior can be attained in a strongly controlled, clean virtual environment to get insights into the origins of observable macroscopic mechanical properties, variability of these properties, and the structure-property relations. Here I'm showing a demonstration of how this virtual lab works, where we have different virtual samples under different loading configurations and simultaneously depicting the progressive damage accumulation. And so, interesting thing about these materials is that they don't normally fail where you expect them to fail at the geometrical stress-induced concentrations. And so different failure occurs because of the mesostructure of this material, which can be studied through the simulations. And so here I'm just showing furthermore the power of simulations, comparing the experimental data sets for a virtual on-notch tensile coupon with simulations to show the close match that we get in strength. And so in conclusion, I have shown here the overarching motivation of using simulation to characterize material properties to accelerate the development of structural parts, the performance characterization of a short fiber composite, and the mechanical predictions for these advanced form of compression molding materials. Thank you for your time.
Thank you, Miguel. So you can see he's well deserved of the recognition. So the winner of the second track, which is the Business in Space Policy, is Josh Wolney from George Washington University, and just recently with Secure World Foundation. And his talk is going to be Policy Challenges to Address the Space Debris Threat. So welcome, Josh.
Hi there, everybody. Miguel and I met yesterday, and he explained his work to me, and I said, wow, policy is basically me making it possible for people who are smarter than me to do good stuff. So that's what I'm here to talk about today. And I was going to spend a little more time at the start talking about characterizing the domain and the challenges. If we get the slides up while I start. But this is such an intelligent crowd, and to save some time, I'm going to click through the first couple, and we don't have to go through the orders and definition. Wow, I thought I was going to be able to do it better, and I'm clicking forward. If I should say next slide, let's go forward one more, and we'll start here. So the goals of this presentation, first I'm going to characterize the orbital domain. I'm going to skip over that a little bit, but mostly I want to outline the three policy areas where space debris is a negative externality. If we look at the chart here on the right from the NASA Orbital Debris Program Office, we see the increase of objects on orbit over time, and if you look at that pink line with the numbers next to it, these represent the challenges that I'm going to talk about today. Number one there is the 2007 Chinese ASAT test, which represented a challenge to international security and also produced a lot of long-lived debris on orbit that's mostly still up there. Number two is from the 2009 Iridium Cosmos collision of two satellites, an American commercial satellite and a Russian old weather satellite, also creating a lot of debris in low Earth orbit. And then number three is a unique challenge to the current regulatory regime, which is just the steady and future much more increased growth of satellites on orbit. And then at the end, I'm going to note the indicators for change in the status quo. So, whoop, I already went in that direction. Situational awareness, we're familiar with it in other domains, air and maritime, where it allows us to operate large objects in limited volume. And the things that we really need there are precise locational knowledge and then also maneuverability. And in these domains, which are significantly smaller than the space domain, going out from roughly 100 kilometers to 36,000 kilometers at GEO, the variables are flipped. In space, we have a huge volume, but we have small objects relatively compared to ships and airplanes, but their maneuverability is either non-existent or very poor or very costly, or also we don't know exactly where everything is. And so this really confounds our ability to deconflict when things could possibly be colliding as we've seen in the past. And so most of the data for space situational awareness comes from the US Department of Defense's Space Surveillance Network, spread mostly across the Northern Hemisphere, using optical, radio frequency, and radar telescopes to sample the environment and track objects. The problem isn't so much the observations. We're not lacking in observations. There's hundreds of thousands every day, but it's the data processing system that takes in that data and turns it into usable information for satellite operators. And so there's a little timeline there on the left showing that the current system was developed in the 1980s on computers half the size of this room. And it was updated a bit and augmented over the next 20 years, but roughly the past 20 years, since the year 2000, there's been a lot of attempts to update and modify and replace, and those acquisition processes have not been very successful. So today, the current program of record is still the SPADOC CaveNet system with conjunction warning messages going out hundreds of thousands every day, or hundreds of thousands every year at least, and error bubbles around objects that might be the size of a car, like making those objects essentially the size of this room or even larger because we just don't know exactly where it is. And so with growing mass on orbit, with growing objects on orbit, what can we do? For international security, do we need treaties? For commercial space, are automatic maneuvers going to be enough? And in the regulatory regime, do we expect to see some new type of action there? Basically, I will answer you at the start and tell you these aren't working right now, and here's why. So space and military activities have always been linked hand in hand. It's dual-use technologies where they have vastly improved civilian life, but they also augmented warfare. And so in this way, the US military has gained an advantage across adversaries across the world. And geopolitical rivals like Russia and China have sought to negate that advantage by developing anti-satellite weapons of various kinds. Meanwhile, the US has also developed similar weapons. And so these big three countries are kind of posturing back and forth, creating these weapons that are really deteriorating to the domain. We're also starting to see these weapons proliferate, not necessarily directly, like these weapons aren't being sold to other countries, but other countries are developing this technology. Most recently, we saw at the end of March, India tested an ASAT missile, which we'll talk about in just a moment. And so with all of this activity, the United Nations General Assembly created a group of governmental experts in 2017, which is a method of work that the UN does to study an issue and get these groups, get the members to talk about what are the challenges in this area, what can we do to move forward to possibly move towards a treaty or something that's going to be beneficial to help the domain in the future. And this was a 2-year work program with 25 member states, including US, Russia, China, and other countries from around the world. And they were going to meet throughout the years to work on this issue and develop the parameters for what would be a treaty. If it were a successful program, the big three would have sat down and found areas where they could compromise and preserve the domain. It was not successful. At the end of March, the program ended, and there's no play-by-play. These are closed proceedings, but from public documents afterwards, we're able to see that there was a consensus report that was written, and in the days leading up to the adoption of the report, the US, either on behalf of just itself or possibly on behalf of other countries who weren't willing to break consensus publicly, the US broke consensus, and therefore the report was not approved and sent to the General Assembly to move forward. And so what we see there is even adversarial nations like Russia and China are engaging in this process, and the U.S. is seeing a way that the main problem that the U.S. had with the consensus report that was they felt it was too influenced by former Russian and Chinese proposals that would have preserved a status quo on orbit that made the U.S. disadvantaged and Russia and China advantaged. So all of these states are acting in their own national interest, but it's creating what I call a gapped status quo, where at the end of March we saw what is allowed to happen. So India tested an anti-satellite missile at roughly 300 kilometers, destroying one of their own satellites and claiming that all of the debris would be re-entered within 45 days. It has now been 106 days, and of the 101 trackable pieces of debris, which are roughly the size of 10 centimeters or larger, which means there's others that are smaller, of those 101 pieces, roughly 50% have degraded, but there will be many on orbit for possibly the next 2 to 3 years still. So this test very much emulates a 2008 US test that struck a similar satellite at a similar altitude using similar technology. And so you have this balance where India is an active proponent of preventing an arms race in outer space, but they're also a US strategic partner and kind of living in both worlds. So this gap status quo is allowing the domain to still be degraded, and progress on a treaty is not moving forward to prevent this from happening in the future. Jumping quickly from the international security domain into the commercial space domain, mega constellations are here, they're happening. At the end of May, the Starlink constellation, the first 60 were launched. And on the left there, those are the proposed and licensed satellites from those companies, all in low Earth orbit, all seeking to provide low latency internet across the globe. Currently, there are about 2,000 active satellites, and so this would represent a huge increase in the number of satellites on orbit. Now, Elon Musk has been quoted saying that the Starlink constellation will have automated collision avoidance capabilities. And we looked into it a little more, and they're saying that they're going to be using a star tracker to precisely know where each Starlink satellite is, and then compare that location to the public catalog to be able to then deconflict. And I don't know if you remember earlier, but the public catalog is lacking a bit right now. So once again, we have this situation where there's increased density and our current activities are not matching what needs to happen in order to deconflict the possible collisions in the future. Then we come to Congress. So the US regulatory system works in such a way that there are 3 agencies that oversee commercial space regulation: the FCC, NOAA, and the Office of Commercial Space Transportation at the FAA, and none of them directly oversee space debris. And so they have conflicting missions, not necessarily conflicting, but overlapping in ways that the Trump administration was seeking to remedy with SPDs 2 and 3, but those, while they can change authorities, they were not able to change budgets without Congress's action. And if you look at the chart, and you can take a look at it later as the slides will be posted, the House committee structure is such that when you're going to move around different authorities, somebody's going to lose out. And so that isn't happening very well. Lastly, indicators to watch. The one thing I want to zero in on is in the bottom right there, increased commercial activity on orbit. This is a place where there's growth, which means that there could be new capabilities that are going to be developed off of the revenue that is created by these companies. If you're SpaceX and you want to not have your satellites collide, you're going to pay somebody to do private SSA or possibly active debris removal. And this is a space where NASA and this community can really lead, because demonstration missions need to happen and there needs to be a proving of those technologies. So thank you very much, and I hope I didn't impress you all too much.
All right.
Thank you, Josh. Appreciate that.
So, for both of the winners, there's Josh, there's Miguel, and why don't we stand right here for a quick photo?
Great.
Go. There you go. Excellent.
Thank you.
Thank you. Congratulations, guys.